Okay, now we have these a standard form, and we have a transfer functions, right? So we know that from the transfer functions, this one is our omega n squared. This is 3 is our 2 zeta omega n. Okay. So once we know this, we can find all these parameters, right? This let me see this not parameters. Okay, we can see the second order parameters. Okay. Okay, now from here we know that our natural frequencies is 2, right? Here. So our set 2, right? So then this is set 2. And then we know that the components omega n here is the component omega n is actually inside this one, so we can find the zeta, right? So that means the zeta 2 zeta omega n is equal to 3 this case, right? So we know that omega n is set 2. We can find zeta equal to 3 see, divided by 2 set 2, right? Okay, so that's equal to 1.06 then, right? So here we know that when zeta is above than 1, right, then we know that the system is overdamped, right? So if we refer back to our previous diagram, we can see that this system is overdamped system, right? So let's test another a value, another transfer function. Let's say we have a system that has a complex number, right? So s squared plus 1s plus 1. Okay, so now this is our omega n, right? This is our okay, this is our omega n squared, right? This is our 2 zeta omega n. Then we can find there omega n equal to 1, and then zeta equal to 1 over 2 just 1, 0.5, right? You see that 0.5, if we refer back to the value of zeta or damping ratio 0.5, it is a complex, right? Complex root. And then it is true if you factor this. If you factor this value, you get the complex root, right? So so now we know that this system is underdamped, right? Underdamped. Okay, let's try another one, which is 1 over s squared plus 0s plus 9. Okay, and then we find that this is 0. That means the whole thing becomes 0. This is our natural frequencies, right? This is our omega n squared, so that our omega n equal to 3. Okay, and then zeta equal to 0. So we know that when zeta equal to 0, the system is underdamped. So we can see that this is equivalent to s squared plus 9, right? So we're going to have a system will have roots, set of roots S1 equal to plus minus J3, right? So which is on the imaginary axis. So that means it is true that when we have this part 0, our system is undamped, sorry. So our system is undamped, right? Okay, it's a bit dark here, sorry, I just put the pattern. Okay. Okay, now you can see that the whole thing start to make sense, because if we have different values, we will have that value will reflect the roots and also reflects the omega and natural frequencies and also the damping ratio, right? So so based on this, we can actually find those parameters like overshoots, like you see in the slide, settling time, peak times, damping ratio, right? So you can refer to the book like chapter 4 in the books that, you know, it show you some, you know, how to get this formula, okay? But it is a simple formula. You see that maybe overshoots, you see that we use the same parameters, right? Overshoot, you can use this. There's a zeta there. So when you know zeta, you can find overshoot, right? So from the transfer function that we have here, for example, so we can find zeta, right? So from that zeta or damping ratio, we can find overshoot. Same thing for here, the settling time. We know the natural frequencies omega n. We know the zeta. Then we can find Ts, right? So Tp, we use pi, we know omega n, natural frequencies, zeta, we can find Tp, all right? And then the last one is zeta. If we can't find from the transfer function, we can use this. If let's say we have information about overshoots, right? We can find zeta from the overshoot, right? Because sometimes some of the questions maybe give you the overshoot values, it doesn't give you the transfer function. You need to, you know, derive that from there. Okay, I hope you understand this, because okay, once we know this, we can simply you know, assume or guess what type of the system that we have, and then what is the performance of the system, right? So I think yeah, maybe okay, let's try to compare. Let's say we have two systems, G1 and G2, right? They have a different set of roots, right? So based on these three parameters, we need to compare overshoot, TP, and TS, because, right, TP, TS, and overshoot, right? So we can see that because zeta is automatically we know that zeta, because zeta is the angle between angle of the vector, right? So let's say now, okay, we have two systems here. We should be able to determine which systems has higher TS or no higher overshoot, something like that, right? These three parameters. You see that the first thing we have to plot this. Okay, this is -1, and then maybe 1. Let's put it. Okay, J1. Okay, minus J1. This is -1. Let's put red color. -1. There's another one is -2. System 1. This is system 2. Okay, this is G2. Sorry, this 1. Sorry. This 2. 1, 2, 2. Okay, this is system 1, system 2, G2. There's another one is G1 is minus 2 here, and then 1 here, right? Okay, this is G1 minus G1. So there are two systems that has a different roots. The first one is this one, right? So you see that when you draw a vector to that point, sorry, you see that value, it's if you compare that with the angle, this angle, you know that the zeta, right? This one has higher zeta, right? This one is higher zeta because as this one move towards this, right? The zeta is going to 0, right? So this one is higher zeta. So this one zeta higher than this one, right? Okay. This zeta is higher than this zeta. Okay, as a result, because if you refer to the formula, right? If you refer to the formula, if zeta is higher, Ts is lower, right? And then Tp is higher, right? So so right now we can say that if this one is increasing, the overshoot is increasing as well, because the overshoot is the function of zeta, right? Okay, so we can say that between these two systems, I just draw again here. Okay, for system 1, alright, system 1 here, system 2 here, okay. So this is G1, this is G2, right? G1, G2, okay. G1, as you can see that G1 has higher damping ratio, right? Star higher because it's moving this side. Okay, then G2, we're talking about G1 and G2, and then G1 has a greater Ts, because Ts settling time is equal to 4 over zeta omega n, right? So here, this is zeta omega n. So this one is higher than this, you see? So that means is G1 has longer Ts compared to this, right? And then overshoot, right? Overshoot, we know that from overdamp has 0 overshoot. As the system moves towards undamped, it is going to be higher overshoot, maximum overshoot. So the overshoot increase by the increase the increase of the angle, or the decrease of the damping ratio. Okay, so that means G1 has, in this case, less overshoot. Okay, G1 has less overshoot, like that. Okay, So from here, from these two systems, you can see by plotting this, knowing these roots, we can roughly estimate which system is better in terms of what, right? In terms of the performance, right? So so we don't have to recalculate again. So the idea is that we need to estimate what is the system performance based on the roots, right, of the denominator of the systems. So knowing that, we can simply change the value of the transfer function, the parameter in the transfer function or the variable, so that we can actually meet the design criteria. Let's say we want something like the system to operate at higher overshoot or higher settling time or something. Okay, and then the same thing, this is about TS and TS. How about TP? TP is moving this way. The higher this point as compared to the other system, the higher the TP will be. So the TP is less compared to this one. So the TP1, this is TP2, right? So TP2 is higher than TP1. If you refer to the formula, if you calculate this, TP1 is lesser. So you see that that point on the imaginary axis, if this one is higher than the other system, that means it has a higher TP. So in terms of TP, G2 is higher, right? G2 is higher than G1. Okay. In terms of overshoot, G2 is higher than G1. In terms of TS, okay, G2 is shorter than G1. G1 is longer than G2. Alright. In terms of damping ratio, you know that G1 is greater than G2. So something like that. Damping ratio, G1 is greater than G2. Alright. I think we stop here. Then we'll do some exercise after this.